In this video, we're going to look at some examples using phasors, and we're going to do some basic circuit analysis. Now, the nice thing here is we're going to just be able to apply all of the analysis techniques we learned in EET1200. In other words, all of those DC analysis techniques, voltage division, current division, Kirchhoff's voltage law, Kirchhoff's current law, nodal analysis, loop analysis, we'll be able to use all of those to analyze these problems. So let's look at an example here. So we have here that the voltage is going to be 10 cosine of 100t volts, 5 ohms here. This is going to be 20 millihenries, and this is going to be 2.5 millifarads. I'm not necessarily worrying about having accurate or realistic values here. I'm just using values that will give us some nice numbers. Now, when doing these circuits here, before we do any of the analysis here or even ask what it is, we're asking for, we're going to need to be doing a phasor transfer. But let's see what the question asks us. It says, find the current in the circuit. Now I'm going to put in parentheses here. Sometimes what they'll do is they'll say find the steady state current. Sometimes they'll leave that off. Sometimes they leave it off just because they're like, well, we're only doing steady state analysis at this point, so when I say find the current, we automatically mean steady state. So what we mean here is we've got some current here, I, and we want to figure out what that is. Now, in order to figure that out, we're going to use phasors, because if I use phasors, I get to put everything in Ohm's law terms, and I get to use all of the analysis techniques that we used in the previous course, and I just have to do some complex arithmetic. All right, so let's see what we got here. The first thing you should always do is do your phasor transform. Transform everything to phasors. So first off, let's look at the voltage source. Now, it's not necessary to do this, but sometimes it can be helpful because we want to make sure we have this written properly. If you have just cosine of 100t, that's the same thing as 10 times cosine of 100t plus 0 degrees. So my phasor for my voltage source would simply be 10 at an angle of 0 degrees. Now, one of the first things I typically do on these problems, it's not necessarily that you have to do it, but I always convert this to rectangular form because my component values are typically going to be in rectangular form, and I typically analyze my circuits in rectangular form. Some examples you'll see worked out, they'll have them worked out in polar form, but I typically work my examples out in rectangular form. So converting this to rectangular, of course we could just use our calculator, but this is an easy one to do, and you kind of almost want to get used to this in your head without having to write this computation down. But it would be 10 cosine of 0 degrees plus j 10 sine of 0 degrees, but that's just equal to 10 plus j0, which we would just write as 10. So this here is 10 volts as a phasor. It seems weird. I'm like, Seems like it's just a DC voltage source. It's not. It's 10 volts as a phasor. It's just a matter of that there is no imaginary part to it. All right, now let's do the phasor transforms for everything else. Well, the resistor is easy because that doesn't change. That's still just 5 ohms. Now for an inductor, remember we need to compute impedances because that's the phasor for an inductor. And this is J omega L. And that's where this angular frequency comes in. Notice here, 100 is what omega is. So my impedance for that inductor would be J times 100 times 20 millihenries, which would be, pulling up my calculator real quickly, 100 times 0.02, because that's what 20 millihenries is, it's 2. So we get J2, and this is still in ohms now. J2 ohms. Now we have 2.5 millifarads. And for a capacitor, the impedance is minus 1 over J omega C, or as I said, I like to use minus J over omega C. So this would be minus J over 100 times 2.5 millifarads. So 100 times 0.0025, and then it's 1 over that, so that's 4. So we have that this is equal to minus J4. Okay, so now we're ready to do our analysis, and there's lots of ways we could do this. Some of you might have an idea already, but I'm just going to do a loop here and add up everything here. So I'm going to go ahead and say, well, if I have a loop, I'll start at the minus 10. So I have minus 10 plus, I'm going to say voltage across the resistor, plus voltage across the inductor, plus voltage across the capacitor is equal to 0. I add up all my voltages. Or we could say voltage across the resistor plus voltage across the inductor plus voltage across the capacitor is equal to 0. But again, here, there's the key thing. With steady state analysis, voltage is equal to impedance times current no matter what the circuit element is. It does not matter whether it's a resistor, capacitor, or an inductor. And clearly the same current is going through everything. So the voltage across the resistor would be equal to 5 ohms times the current. Well, what's the impedance for the inductor? It's J2 times the current. And then the impedance for the capacitor is minus J4 times the current. And this should not be 0 here. That should be 10. You probably already caught that. Equals 10. Now, all I have to do is factor out this I and combine some like terms, and I'd have 5 minus J2 times I equals 10. And so I is equal to 10 divided by 5 minus J2. And now this is where, again, it's useful to have a calculator that can do complex numbers for us. And so I'm going to go back to the calculator online, and it's 10 divided by, parenthesis, 5 minus 2, and because I'm putting in a calculator, I got to actually use the I. And then it spits out an answer for me of, it's doing it as fraction 50 over 29 plus 20 over 29 J. And this current would be in amps. Now, we want to write our final answer down, and when we write our final answer, we're going to want it in terms of the cosine, so we're going to want to convert this back to polar. So I'm going to pause the video while I convert that back to polar. And so when I did this, I got 1.86 at an angle of 21. And let me go to the website that I used here to make sure. 1.86, 21.81 degrees. And this would be amps. And now we want to write this as my current here. So the current would be 1.86 cosine. Now the frequency is still the same, 100t, plus 21.81 degrees as my phase shift. So yeah, there's definitely more computations involved, but what I really want to show you with this example is, notice that we really aren't doing that much different than what we did in the previous course. We're just now having to use complex numbers. And in some ways, I think it's kind of fun, because now I can use capacitors and inductors and see what the outputs are without having to write these meshy differential equations in, or getting these RC time constants and everything. So it's a neat little way to do that. So let's look at another example here. Let's look at this one here. Not plus minus there, because I want this to actually be a current source this time. Okay, so in this case here, we're going to be asked to find V out. And I'll have here that, we'll just ask to find V out here. This is in amps. Okay, so let's go ahead and look at this problem here. Well, first off, just like we do with every one here, we need to transform this into phasor format. And so I should notice, though, first here, notice again, you have to be careful. What am I given? I'm given a sine function. So I need to rewrite this first as 5 cosine of 35t minus 10 degrees minus 90 degrees amps, which is 5 cosine of 35t minus 100 degrees amps. Now, of course, you could obviously skip this step here, but I want to show you all the work, which then means my phasor for my current, IS, capital IS, would be 5 at an angle of negative 100 degrees amps. And again, I'm going to go ahead and convert this into rectangular form, because actually, no, in this case, I'll show you can do it either way. I'm going to leave this in polar form here, because you can do these in either way. And I'll show you how to do that. Okay, so we now need to find the impedance of my components here. Well, the impedance of the resistor is easy. That is just still 6 ohms. And the impedance of the capacitor is equal to minus J over omega C. And in this case, this would be minus J. Well, where's my omega? That's 35 times 0.01, which, let me make sure I don't make a silly mistake on my calculator. And then do the reciprocal of that. And we'll round that to 2.86 minus J 2.86 ohms. Okay, now I said everything is, I'm going to leave this in polar form, because as I said, you can do these in either rectangular or polar form. I prefer doing them in the rectangular, and which is what I'm going to do most of my examples. But I thought I'd show you that you can do these in polar. So to do these in polar, you would have to convert to polar. But here's a quick table, because converting components to polar form is easy. So here's a quick table that you should maybe write down. If you have a resistor, Z sub R in polar form is going to be R at an angle of 0 degrees. If you have an inductor, the polar form will be whatever the impedance is you computed for the inductor at an angle of 90 degrees. And if you have a capacitor, it's going to be the capacitance impedance at an angle of minus 90 degrees. And I'll sketch a little graph here to show you why. So think of this as the imaginary axis, and this is my real axis. Well, resistors are completely real, so that's 0 degrees. Formula for an inductor is J omega L, so that's always going to be here. So an inductor is always going to be on that positive J axis, so that's always 90 degrees. And a capacitor is negative J over omega C. Well, negative J is always going to be on the lower portion of the J axis there, so that's always going to be minus 90 degrees. But you could put this little table down as well to help. So that actually makes converting these to polar form really easy. That's just 6 at an angle of 0 degrees, and this is just 2.86 at an angle of minus 90 degrees. So let me write those in here. 6 at an angle of 0 degrees. And this is, I'm sorry, I'm writing it in the wrong spot. 6 at an angle of 0 degrees. And this is 2.86 at an angle of minus 90 degrees. All right, so again, we have all of our analysis techniques available to us. And what I would notice here is if I make this ground down here, I really just have one unknown node. And I know from nodal analysis that the current coming into a node is equal to the current leaving. So if I draw two currents going down here, I'll just call this the current going through the capacitor, the current going through the resistor. Then we know that IS, since that's coming into the node, is equal to IR plus IC. And so we'd have 5 at an angle of negative 100 degrees is equal to, well, if I think about this, as far as voltages are concerned, well, this would be the output voltage divided by the resistance, or the impedance. So this would be 6 at an angle of 0 degrees, plus the output voltage divided by 2.86 at an angle of 90 degrees. So now I have just a simple equation, one unknown. Now, I still have to work with some complex numbers here. And what I'm going to multiply both sides by here, I'm going to multiply both sides by 6 at an angle of 0 degrees times 2.86 at an angle of 90 degrees. I'm going to multiply both sides by that. So I'd have 5 at an angle of negative 100 times 6 at an angle of 0 degrees times 2.86 at an angle of negative 90 degrees. And this is equal to then, well, this 6 at an angle of 0 degrees would cancel out, so it'd be V out times 2.86 at an angle of negative 90 degrees. And then these 2.86s would cancel out here, and so it'd be plus V out times 6 at an angle of 0 degrees. Now we can go through and do this multiplication. You have 5 times 6, 5 times 6 times 2.86, which is 85.8 at an angle of negative 100 plus 0 minus 90, negative 190 degrees, is equal to V out times 2.86 at an angle of minus 90 degrees plus 6 at an angle of 0 degrees. Now remember, adding these in polar format's not necessarily the easiest thing to do, but you could use a calculator to do that. Or remember that one homework problem I had you be working on in the first module, where I was having you do all sorts of complex numbers. We could write this as V out is equal to 85.8 at an angle of negative 190 degrees. Whoops, my hand hit something here. Divided by 2.86 at an angle of negative 90 degrees plus 6 at an angle of 0 degrees. Okay, so I'm going to pause this while I do this on my calculator. So when I got this here, I had in the denominator 6.65 at an angle of 25.5 degrees, and my numerator was 85.8 at an angle of negative 190 degrees. And now I can just do this division here. And how did I do that? Well, I used my calculator, but here I'll even show you. Actually, what I did is I used a little website here. I'll just leave it here for a second. You know, you could copy down the website there or type it in. You can't copy it because you can't do a copy and paste on a video, but you could clearly pause it and write that URL down if you want. Or I'll hit the back arrow. I just did polar calculator, and it was the first result. And then I just put the things in there and said I wanted to add them together to see what we get. And now doing this simple division here, we know we can just do this here. So this would be 85.8 divided by 6.65. So that's 12.9 at an angle of, well, it would be negative 190 minus 25.5 negative, which is negative 164.5. And of course, these units would be volts. And so now we can write our final answer as 12.9 cosine of 35t minus 164.5 degrees volts. Now, I did this example using polar notation. I'm probably never going to do that again because you have the polar addition and everything, which can kind of get, as I said, a little messy. But I want to emphasize, and maybe you want to do this as a practice, you could do this using non-polar coordinates. So let's go ahead and show what we'd have here as far as what you would be doing here if it was non-polar. Let's change this diagram a tiny bit and show what you would be doing, and your equations would be different, but the process would still be the same. So what the heck happened there? That's not right. So let's try this again here. Okay, here we go again. -100 cosine times 5. That's not right. I'm trying to use my keyboard, and I think that's what the problem was. 100 negative cosine times 5. I guess it is negative 0.86. I kept doing it over and over again, but so we'd have negative point, what is that? 868. Negative 7.88. So you'd have this here would be your current, and then you would use this number and this number for your impedances, and then you could still use the same nodal analysis technique to solve the problem. Now we will do more examples of this. This is not the last example, but I just wanted to do some starting ones here.